Welcome back to An Ape's Guide to Human Language. We are framing our question for this entire semester on what it is about human language that makes language special. And we're taking the perspective of this curious primate who's looking at humans and wondering, what is it about the things that humans do with language that is special? I mean, after all, we're all apes together. So what is it that makes human communication so effective? What allows humans to go forth and communicate with each other in such a way that we can send other apes to the moon? So one of the ways we're going to ask this question for today's lesson is something to do with the sounds of the communication system. So an ape might be wondering, maybe it's something to do with the sounds of human communication. Are they special in some way? So just as a recap, we've started talking about how the anatomy of the human vocal tract is heavily involved in the types of articulations that humans can make. And we've been learning to name the different articulators from the very front of the mouth for the bilabials, all the way back to the velum, that soft palate tissue, and even down as far as the glottis. So we went through last time very quickly the consonant phonemes of English, and you can follow up with these in your readings as well. We spent a little bit of time talking about the different places of articulation and a little bit of time speaking about the different manners of articulation. So if you want a little bit more detail, again, you can check back in your textbook for a bit more detail about the different ways of manipulating the airstream to make different kinds of sounds, to describe the different manners of articulation, the stops, the nasals, the fricatives, the affricates, and the approximants, which for English include liquids and glides. So this is a lot of text about like how we describe the different properties of the speech sounds that we know and use in English. But why do we keep talking about phonemes? Like, what is a phoneme, and why not just call them sounds? Well, the important piece for us to deal with is the idea that phonemes are groupings of sounds where individual sounds are treated together as though they have just one function. So within each linguistic system, there are functional groupings of sounds. And I'll explain a little bit more about what I mean by this in the next couple of slides. So we might want to start by asking ourselves a question. How many l sounds are there in English? So if you think about the way that we write words and the way that we think about the sounds that go into words, you might think, well, there's only one way of saying l, right? I mean, there's only one letter for it. But over here on the right-hand side, I've got two pictures of things that we might be able to name that have l sounds in them. So one of these sounds goes a little bit like this. Lee, 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 lee. And now I'll name the other object that you can see a picture of. Eel, 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 eel. Now, even if I join those words up completely without any gaps between the words, lee, 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 and eel, 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 there's still something about those sounds, the in lee and the in eel, that makes them sound somehow different. Now, I should say that this is a feature of my variety of English, and it may not be true for all of you, as we all speak slightly different varieties of English around the world. But in my variety of English, we can write a little rule that describes these two different l sounds. So here in the angled brackets on the side, we have the l category of speech sounds. And in our variety, if we can hear those differences, then we can actually write them with different symbols in the International Phonetic Alphabet, which has come up a little in your readings. So one way of pronouncing the l phoneme is the l that we heard just before. It's the one that comes before a vowel, like in light and leap and lovely. There's also a second way of pronouncing l sounds, and in my variety of English, it comes after a vowel. So this is the one in milk and fall and ball. So we have a l and a l, and they sound just a little bit different. Now we might want to ask ourselves, well, maybe we just have two categories of L sound. If they sound different from each other, maybe they're just different, and we could call them two categories. So I've got two words here, love, which has the light L, like the one before, a vowel in light and leap and lee and lovely. And I have milk that has the dark L that comes after the vowel, milk. So I'm going to do a substitution test. I'm going to see whether if I swap one of the L sounds into the other position, whether it's going to make it sound like I have a different word there entirely. So first of all, I'm going to take the light L from love and put it in milk. 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 So you see with that light L, my tongue's in a slightly different position and it just comes out sounding like milk still, but a kind of a differently accented milk. It might sound like a Scandinavian kind of accent of some sort or a Swedish accent. Now if I try swapping the other way around and I take the dark L from milk, the L sound, and put it in love, love. Love. It doesn't change the meaning of the word at all. It does make me sound a lot more like I have a very Australian accent though. So as I mentioned, the different varieties of English can have different combinations of sounds playing the same functional roles. But let's try a few alternative substitutions. What happens if we change some of these speech sounds for other sounds that are a little bit more different? So I'm going to swap each of these different phonemes into the position at the beginning of the word love. So we started with love, and it's a completely fine word. It's also the same pronunciation that you might hear in some of the northern British accents, like the Beatles accent when they have lovely. Okay, so we've tried the dark L and it does not change the meaning of the word at all. But if I put the D sound instead, dove, suddenly we have a different word. And if I put the G sound as in gov, suddenly we have something that sounds like a government website. So those first two substitutions clearly come from a different category because they make us think of a different word rather than the word we started with. So these are what we would call minimal pairs in English. These are pairs of words that differ by just one sound, where if you swap that sound, you end up with a different meaning. So now if we go ahead and do a few more substitutions, we can swap in sav and zav and nav and pav and buv. Now, none of these make good words, but when we hear these sounds, we don't think we're hearing the word love. We think we might be hearing some made up word or the name of a cartoon character, or perhaps a new product that we're just not familiar with. So this tells us that these other sounds like s and z and n and p and b come from a different functional category. They're playing a role that helps us distinguish sounds in meaning. And that's why we can call them different phonemes. Now, I mentioned before that different varieties may have different ways of forming these functional groupings. So in my variety, we have the light L before the vowel and the dark L after the vowel. In the Singapore variety, there's a bit of variation, but a lot of people, for the L sound that comes after a vowel, they tend to articulate it with a different kind of sound again, something more like ball or fall, that doesn't have the L-y sound that I'm used to. Now, I'm not very good at saying it, so apologies for getting it wrong. But in general, what we're trying to come to terms with here is the idea that a phoneme is a functional grouping of speech sounds within a language that are used together in a particular way. So if we want to put that in a formal definition, we can say that phonemes are abstract categories of speech sounds that have functional equivalence for people who are speakers of a language. The kind of evidence that we've used to look at today is the idea of phonemic contrast. So pairs of words that differ by just one sound, where if you substitute those sounds over, you get a totally different word meaning, or you get a totally novel word that hasn't been encountered before. Now we might want to ask ourselves, if we're a very critical kind of ape, do these phonemes really exist? How do we know that the way that we perceive them is truly categorical? So a classical definition of categorical perception is the idea that sounds might exist on some continuum, like colors in a rainbow, where although the gradations between one sound and the next are completely continuous, they're perceived as though they chunk together in certain functional groups. So the difference between sounds within a category might seem unimportant, but a difference of the same magnitude that straddles a category boundary might seem very important. Now, in your own homework, you've been discovering a little bit about how difficult it is to match the movements of a novel set of articulators to the categories of the speech sounds that you're familiar with. But let's think for a moment about the process on the other side, the process of perception. So we're going to start with a feature of articulation that we haven't spent much time with yet, and this is called voice onset time. So voice onset time is a property of the stop consonants. So remember that stop consonants are the ones where, as your articulators close, the airflow coming up the trachea is still continuing. So there's a little buildup of pressure in the mouth. And as the articulators are released quite suddenly, that air punches out, causing a pressure wave that is quite rapid. So in the stop consonants, depending on the timing of when we initiate voicing, when we start vibrating the vocal folds at the glottis, we could actually start those vocal fold vibrations before the closure has been released. And if we do this, we get something called pre-voicing. So I'll give you an example with the words gap and cap. So for a pre-voiced example, I might start the voicing before I open my vocal tract at the velum. So gap, gap. Now I'm doing it very exaggerated at the moment, just as an example. But when we normally say gap, the timing of the onset of the vocal folds and the release is very close together in time, or at least closer together in time than I was doing for you just then. So we might get something more like gap, gap, or gap with a little bit of pre-voicing. If instead, so remembering that gap and cap are articulations made at the velum, so the back of the tongue comes up and touches the soft palate before releasing. So if I take a little bit of time after releasing, before I start the vocal folds vibrating, I get cap, cap, right? So the articulators have opened up, a little bit of air pops out, the k sound, followed by the vibration of vocal folds. I can do the same at the bilabial place of articulation with beach, 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 and peach, peach, or a very hyper aspirated version, peach. Okay, so you can see we have a spectrum of speech sounds that can go all the way from very pre-voiced to very aspirated or post-voiced. And we can see this spectrum in the little chart we have here, from -20 milliseconds up to +40 milliseconds. And the little puff of air is sometimes expressed in phonetic notation with a little sound to indicate the audible airflow. Now, in my variety of English, the boundary between sounds that we think of as g and sounds that we think of as k falls around here, somewhere close to 20 milliseconds post release of the closure. Now, for some time, psychologists have been investigating how is it that we perceive these different sounds. Is it that when we hear sounds down this end, they sound very much like one category, and sounds at this end of the spectrum, they they sound very much like another category. And then somewhere in between, we have a sudden changeover? Or is it more the case that in the middle of the spectrum, we have things that sound a bit like a beachy peach or a peachy beach, and we're just not sure? So the first investigations into these phenomena were carried out by Liska and Abramson way back in the 1950s. And they took a voice onset time, VOT spectrum, just like the one we were talking about before, and asked adults to do two different kinds of tasks. The first kind of task was a categorization task where they simply had to say, is this a B sound or a P sound? This is also known as a phoneme identification task. The second kind of task that they asked people to do was a discrimination task where they would take pairs of sounds from different places on the continuum and ask people, are these two sounds the same or different? Are these two sounds the same or different? Are these two sounds the same or different? So in the model of categorical perception, the important properties of the categories are these ones you can see over on the right here. And the idea is there are some sounds at one end of the spectrum that always sound like they have one identity. So in this case, we would see that sounds at the very beginning of the spectrum are never classified as P, always classified as B. And then later on in the spectrum, we have the exact opposite. So some sounds are always categorized as P and never as B. When people are asked to do the discrimination task, we get a different pattern of events, which we can see on the right. And what happens in this case is when sounds are drawn from within one category, people have great difficulty telling whether or not they were the same or different. And it's kind of as though those two sounds have fallen into one bucket and we can no longer figure out the minor details that might make them different from each other. When we get to the category boundary, however, we get very, very good at telling the difference between these two categories. So we see this peak in performance followed by a drop to 50%, where people can no longer tell the difference. In our own lab, we've been conducting studies on how these properties of speech perception work for bilingual Singaporean adults. Now, some of you may have actually taken part in this study and you may recognize these stimuli. For those of you who didn't get a chance to take part in this fun study, we designed a perception task exactly like this Liska and Abramson one that you've seen before, using the target words peach and beach. And the task is designed to be child friendly, so we can run it with adults as well as with children. And the goal of the task is to help this little monkey to collect a bunch of flowers for his crown. And on each trial of the game, our participants will hear one speech sound drawn from a VOT continuum. So our voice onset time continuum goes from -60 milliseconds to +90 milliseconds. So I'll play the -60 sound for you now.
Beach.
And if you can hear that sound before the beach begins, that pre-voicing, I'll play it again.
Beach.
And one more time.
Beach.
At the other end of the spectrum, we have a long delay between when the mouth is released and we have that little puff of aspiration and then the voicing begins.
Peach. Peach.
At the simultaneous point where there is 0 milliseconds delay between the opening of the closure and the timing of the voicing, we get something that sounds like this.
Beach.
Oh.
Beach.
And I mentioned that for my variety of English, the category boundary falls around here, close to 20 milliseconds. So let's have a listen to one of those examples and we'll see whether you instantly categorize it as a beach or a peach or have some uncertainty in your decision making.
Beach. Beach.
Let's hear the next one.
Beach. Beach.
Okay. Now, the reason I'm sharing this with you is so that I can show you some of our preliminary results, because it's one thing to see a paper from the 1950s, but it's much more interesting to see some descriptive work that is actually showing us what these patterns look like in ourselves or our classmates. So on the next slide, you're going to see a voice onset time continuum. And just like in those schematics that I showed you before, we're going to be looking at the percentage of PERT choices, right? So here's the theoretical model here, where we see the percentage of PERT choices starts off at one end of the spectrum very low and at the other end of the spectrum very high. So let's have a look at some real data from Singaporean bilinguals. So here's the voice onset time spectrum across the bottom in milliseconds. So from very pre-voiced to very aspirated. We have 0 milliseconds over here, that simultaneous voicing point. And this is the percentage of PERT choices. And you can see that although there's some variability in our group, this was our very first pilot sample. Although there's some variability among individuals, we can see this very characteristic pattern where the vast majority of decisions are for one category, then there's a switch, and then there's another category. It's maybe not quite as steep as the theoretical model would predict, but on the whole, this is very steep. The other characteristic that I want to share with you is what's going on for these tokens around 20 and 30 milliseconds. How do people change in their performance when they're at this category boundary? And it might be peach or it might be beach. As we can see from their responses, they're around 50%. This time what we're looking at is a reaction time plot. So these are the same time points on the VOT continuum. And what we can see now is how quickly people make their decisions. And what we can see is that they're very, very stable in making their decisions at very close to 500 milliseconds, except when they hit that category boundary between 20 and 30 milliseconds, we see a slowdown. And this is very significant. So this tells us, this slowdown at the category boundary tells us that the categories have like prototypes. They have some versions of themselves that are just better. So there are buzz and pers. There's just really good ones. And then there's some degree of overlap at the category boundaries, meaning that they have kind of fuzzy edges where it's difficult to tell the difference between these two tokens. What we were also interested to find out is whether or not a bilingual who may speak more than one language, whether across their languages they have sort of grouped together all of this acoustic information into just one pattern, or whether they have separate patterns for their two languages. So again, this is our data that is still in progress, and some of you may have taken part in this study, but it's nice to have a little sneak peek at the results. So obviously, if we're asking people about peach and beach, that's a very English language task. So we had to come up with an analogous task for our little monkey to perform, only this time around we used Chinese. So you can see the task at the top. We have our beach and peach, and we have our Mandarin Chinese, which I'm terribly sorry, I'm probably going to say incorrectly, but along the lines of B and P. And what we can see here is all of our participants. This was the full-scale study, so we had 66 participants this time. And what we can see here is those trajectories that start low at one end, end high at the other end of the VOT spectrum, with a steep transition in between. And we can see in blue the individual responses for English, and in red, the individual responses for Mandarin. So these are all the same people tested on 2 different days. So what we see is that people have 2 slightly different representations across their 2 languages. And in general, the Mandarin responses come just a little bit later than the English responses. Now, this is not impaired performance by any means. It just tells us that the category boundary comes at a different place in time. So this is telling us that the human mind is capable not just of grouping things into two categories, but forming two totally separate representations of how to group these sounds into two categories, depending on the language that we're listening to. And this is a very sophisticated skill. So clearly, it's possible to have more than one category, even more than one category of speech sound, but on top of that, multiple categorical representations. The question that our curious ape might be asking at this point is, where does this grouping together come from? When do we learn about how to group these sounds together? Well, in your developmental psychology, you will probably remember that prenatal auditory development begins even before birth. And if we wanted to simulate what the prenatal auditory environment would be like, we would have to take out some of the sounds that we out here in the air can hear. So this is an example of what it might be like to hear speech through the wall of the womb. So what you can see here is that the sh, t, k, p sounds are completely absent from this speech. Whereas over here in the spectrogram, we can see the low frequencies and the high frequencies. There's all sorts of information going on throughout. The little blue line though tells us about the pitch, which means the up and down parts of the voice. And these are preserved quite well. So we know that babies before they're born have access to pitch, and they also have access to loudness. So they have something about the rhythm of speech as well. But in these voice onset time categories that we've just been looking at, what we're really looking at is the timing of pitch relative to a high frequency component, right? So the timing of the voicing relative to some of those like breathy parts of speech. So how do babies do? Well, it turns out pretty well. So you may recall this study from your developmental psychology. 4-month-old babies, when tested on pairs of sounds from either within a category or across a voice onset time boundary, perform differently. So these are all pairs of sounds that differ by 20 milliseconds in their timing for the voice onset time. And in the first chart here, we can see babies who are being habituated to sounds that are from, habituated to sounds from one category, and then at the dotted line they're exposed to a sound from a different category. And you can see that their sucking rate, a physiological measure of their arousal, suddenly jumps up. In the second little plot here, you can see what happens when they're habituated to just one sound from among this continuum, and then they're swapped to a different sound, but from within the same category. So there's hardly a difference at all, and not a significant one. And then in the third case, they're habituated to one sound, and that same sound continues playing. So we can see this jump in arousal of 4-month-old babies tells us that babies have this sensitivity to category boundaries. So categorical perception is clearly possible from early in development. What we might want to ask then is, does anything change? So let's look at some data from some different languages. So the first contrast we're going to look at is the difference between ta, ta, ta sounds, the t sound at the alveolar place of articulation, and ta, ta, ta sounds, which are at the retroflex place of articulation. So on our little anatomical model here, you can see that they both use the alveolar ridge, but in the alveolar sound, the tongue tip is making contact with the alveolar ridge with its upper surface. However, the ta, ta, ta sound. Now, For the retroflex, the tongue tip has flipped over and is making contact with the undersurface of the tongue, ta, ta, ta. Right, so even though it's at the same place on the alveolar ridgeline or very close by on the alveolar ridge, the orientation of the tongue means that the sound comes out sounding different. Now, I'm sure in isolation, you guys can probably hear the difference between ta and ta. I'll do it one more time. Ta, ta. But it's very hard to hold these differences in mind at high speed or when you have to make lots of decisions about them, unless this is a sound that's used in your languages. So for speakers of Hindi and speakers of Tamil, this contrast is an important one. Let's see how babies do compared to adults. So on the left-hand side here, we can see Hindi adults are 100% at always telling the difference between these two sounds. At 6 to 8 months of age, American English-speaking babies are also very high performance, but English-speaking adults are down at 10%. Now, when this paper first came out in the 1980s, some people questioned, well, maybe there's something about your test that is not working very well, or maybe you've only demonstrated it for this one sound. So the same researchers came back and had another look using the same sound over a wider range of babies, including native learning babies from the same communities. And a second contrast, which is shown up here between the velar ka, 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 ka sound and the uvula, which you can see in the second green line here. So that little dangly bit at the back of the soft palate. So that's a little bit more like ka, 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 ka. So ka, 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 ka. Okay, so let's see how our babies and our adults do this time around. So in this data set, what we see is 6 to 8 month olds are very good at both contrasts. 8 to 10 month olds, these are English speaking monolingual babies in America for the first few bars. The monolingual babies are very good at around 6 months, a little bit less good at around 8 months, and a little less good again at 10 to 12 months. But children who are growing up hearing these contrasts within their languages, so the Hindi infants for this contrast and the Salish infants for this contrast, at 11 to 12 months, they can hear the contrast that is in their own native language. So this is just to show that it's not like the test is not get writable for children of this age. They can clearly get it right when it's a contrast from within their own language. So this is telling us something about how the auditory system adapts to the linguistic environment. Another data set that tells us a lot of wonderful information about this is a data set from Patricia Kuhl's lab that investigated the perceptual quality for Ra and La for babies from different language backgrounds. And this is the killer plot where at 6 to 8 months of age, we can see that two groups of babies, American English exposed infants and Japanese exposed infants, have exactly the same performance level at 6 to 8 months of age at distinguishing between Ra and La. But if you come back just a few months later, suddenly there's a big difference. The American infants have gotten better at telling the difference between Ra and La, and the Japanese infants have gotten worse at telling the difference between Ra and La, and they are heading towards 50%. And what this is telling us is that for the American infants, they started out with some weak ability to tell the difference between these two speech sounds. And then with exposure, those categories have strengthened and become more different from each other. Now, the Japanese infants are not hearing at all, and they're not hearing at all in the language that they're exposed to. Rather, they're hearing a different sound. They're hearing ra, 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 ri, ru, re, ro, right? And that alternative sound, the tap sound, sits in a very similar acoustic space to the ra and the la sound, but isn't the same as either of them. So by tuning in on the way that ra sounds, it's as though ra is treated as one of those like fuzzy bad examples of ra, and la is treated as a fuzzy bad atypical example of ra. And so they are grouped together, all of them, as though they are one category, whereas for the American infants, they're hearing them as though they are two categories. So this model is known as perceptual attunement. And the idea is that when we first come into the world, we have some way of sensing differences between different stimuli. And with exposure, that perceptual map distorts in line with the structure of our environment. So there is this gradual reshaping of auditory representations. And this is happening at a really exciting time in neuroplastic development and change. So when we model the kind of patterns of neural connectivity over the first few months of life, we see that newborns start out with relatively sparse connectivity patterns in the cortex. And then over time, there is this proliferation of the dendritic arbor that allows new patterns of connectivity to better represent the sounds that are going on in the environment. So the neural commitment processes that we've seen in these last few examples for language-specific tuning seem to be really kicking in between about 6 and 12 months of age. So, says our curious ape, human babies learn all the sounds they need by the end of the first year, and then they are done. That has been the dominant story for a really long time, but we need to bear in mind that sometimes when we use more sensitive methods of measuring things, we can actually start to see how long it takes us to truly lock into the patterns from within our speech communities. So just to take us back one more time to the Peach Beach study with the monkeys, this is what happens when we look at those patterns of acoustic development between adults who are bilingual in English and Chinese in Singapore and children in Singapore doing exactly the same task. Now, I'm just going to share with you the data for English for this next slide. So what we can see here is 6-year-olds on the left and adults on the right. And we saw those perceptual tuning curves earlier, where the adults have this very steep transition between hearing things that sound like beach and hearing things that sound like peach. But what we see when we look at the kids is this much less tightly tuned slope, right? The kids have these categories, but they seem like they're much fuzzier. The prototypes aren't quite as strong yet. So their slope shape is a lot lower. And there are some kids who maybe really are struggling to hear these differences still. And when we look down at the bottom at these reaction times, we can see that the kids on average, apart from just being generally a bit slower to push the buttons in response to the stimuli. So they're up here at 1 second rather than the adults down here at around ½ a second. The adults show us this really steep characteristic slowdown at the category boundary. And this is like individual by individual. If we check where is the category boundary for one individual, are they slower at that time point? And for our adults, the answer is yes. But for the kids, there might be a few kids who are showing that pattern, but the majority are not there yet. So this is really telling us something about the trajectory of language learning in human primates. even when we think just about these phoneme categories, it takes some time before children's hearing is aligned with the targets of adult speech and functions in the same way as adult speech, with the same speed and precision as adult perception for speech. So I'm going to chop this mini lecture here, and I will see you back shortly.